In this video, we're going to introduce vector functions and space curves. So by a vector-valued function, or more simply, a vector function, we just mean a function that takes a real number input and assigns a vector output. We've already seen one type of vector-valued function, and that's when we wrote the vector form of an equation of a line. More specifically, if we have our vector r0 is the vector x0, y0, z0, and v is our direction vector ABC, then we wrote the equation of the line in vector form, r0 plus t times v, or as the components go, the x0 plus ta, comma y0 plus tb, comma z0 plus tc. More generally, any vector-valued function can be written in the form of r of t equals f of t, g of t, h of t as the components. Here is in the ijk form. Those are equivalent to each other, of course. We refer to the functions f, g, and h as component functions of r of t. And much of our work with vector-valued functions will be concentrating on these component functions. So as an example here, let's look at the vector-valued function r of t equals natural log of 2 minus t, t over 1 minus t squared, and e to the t, and it asks us to write down what the component functions are and then express the domain of the vector-valued function. So our component functions are f of t equals natural log of 2 minus t. That's the x component, if you will. Our y component function is t over 1 minus t squared, and our z component function is the e to the t. And given the fact that we wrote it as f, g, h before, we're using that same notation here of f referring to the x component, g referring to the y component, and h referring to the z component function. When we're looking for the domain of the vector-valued function, the value that we plug in for t has to be in the domain of all three component functions. So we notice that for the natural log function, we know that the natural log must be positive. The input must be positive for a natural log. So our 2 minus t has to be positive, or t has to be less than 2. It has to be strictly less than 2 because we cannot plug in 0. So our domain for f of t will just be the interval from minus infinity to 2. For g of t, we notice that we cannot have a 0 in the denominator. So namely, t cannot be either negative 1 or 1. So our domain is the union of the intervals negative infinity to negative 1, negative 1 to 1, and 1 to infinity. And of course, all of those intervals are open. And then the domain for h of t is all real numbers because there's not any domain issues with plugging things into the exponential function. So we said that the domain of the vector-valued function had to be numbers that were in the domains of all three. Well, certainly, we have to stop at 2, because we can't get any bigger than 2. We also have to eliminate negative 1 and 1 for g of t. So our domain in this case becomes the interval from negative infinity to negative 1, union the interval from negative 1 to 1, union the interval from 1 to 2, and again, all open intervals in that case. As I mentioned previously, we are going to look at analyzing these types of functions by their component functions. And in particular, we'll analyze the component functions the way we did back in first semester calculus. So back in first semester calculus, our very first topic was limits. So let's go with limits of vector-valued functions. So if we have a vector-valued function written in its component form, then the limit as t approaches a of the vector-valued function is simply the vector that you get when you look at the limits as t approaches a for all three component functions, provided that all three of these functions have limits at that value. So let's look at the limit of the vector-valued function t squared minus 4 over t minus 2 times I, plus t minus 2 over natural log of t minus 2 times j, minus cosine pi t times k. We want the limit of this vector-valued function as t approaches 2. So, according to our definition, the limit of the vector-valued functions is going to be the vector whose components are the limits of each of the component functions. So we'll evaluate each component function's limit as t approaches 2. So our first component function, we'll notice that we had the t squared minus 4 over t minus 2. we can factor the t squared minus 4 as t minus 2 times t plus 2. And then notice that as long as t is not equal to 2, we can cancel out the common factors of t minus 2. For the second component function, we'll use L'Hopital's rule to evaluate the limit. Derivative of the top is negative 1. Derivative of the bottom is negative 1 over 2 minus t. And I guess technically with this limit, I should have said as the limit t approaches 2 from the left, because the natural log function isn't defined as t approaches 2 from the right. But we'll just treat that as a typo for right now. And then for the third one, we have the limit as t approaches 2 of cosine of pi t. There's no issues with cosine, so we'll be able to evaluate it by direct substitution in a minute. As we mentioned before, the t minus 2's factors will cancel in the first component, the first limit. So we have the limit as t approaches 2 of t plus 2 times I. In the second component function, that limit simplifies to the limit as t approaches 2 of 2 minus t. And in the third one, we didn't do anything, so we still have the limit as t approaches 2 of cosine of pi t. We can evaluate each of these limits now by direct substitution. The limit of the first one gives us 4, the second one gives us 0, the third one gives us 1. So we'll get 4i minus k as our limit. As a quick definition that goes along with limits is continuity. We say that a vector-valued function is continuous if each of its component functions is continuous at the t equal to a. Or more generally, or maybe more specifically, whichever way you look at it, if you can evaluate the limit of a vector-valued function by direct substitution. That tells us that we are also continuous at that particular value. All right, so let's switch over to doing graphs of vector-valued functions. We know that if we have a set of component functions for a vector-valued function, we can define the equivalent set of parametric equations, if you will. X equals f of t, y equals g of t, and z equals h of t. If we have a particle that has that position at time t, then we can imagine the curve being traced out by the position of that particle as the t increases. Or if we think about that point as being the tip of the position vector of the particle at time t, then another way we can describe that path is just by tracing the tip of the vector out as t increases. So let's do a specific example to see if we can illustrate this point. Let's sketch the curve defined by r of t equals the vector t squared. Well, the parametric equations are x equals t, y equals t, and then z equals t squared. First that we notice is that the x and the y coordinates are always the same, no matter what we plug in for t. The x has to equal the y. So that means that the curve has to be in the plane x equals y, because those first two components are the same. All right. We also notice that if we just look at the x equal to t and the z equal to t squared, we can write that equivalently as z equals x squared, and that's a parabola. So what we end up with is a parabola that's actually in the plane x equals y. So here's a graph. The red axis is representing the x-axis, the green axis is representing the y-axis. So our plane x equal to y is this lightly shaded rectangle, if you will, and it's going backwards through the origin this way. It's a little hard to see the depth in this one, just the way that it's drawn out. But you can see the curve. This is the parabola, and we can definitely see that it's diagonal with respect to the xy plane, if you will. And as t increases, the x-coordinate increases. So we have to be going back to front when we draw the curve. Let's do another quick example. Let's find a vector-valued function that represents the curve of intersection of the surfaces x squared plus z squared equals 9 and y equals x times z. Well, notice that the x squared plus z squared represents a circle. We can parameterize circles pretty quickly by using cosine and sine. If we let x equals 3 cosine t and z equals 3 sine t, then we get a parameterization of the circle. Also, if x is 3 cosine t and z is 3 sine t, then y is just the product of those two things, and so we get y equals 9 sine t cosine t. So now we have an x, a y, and a z component for the curve of intersection. So we can write the vector valued function as r of t equals 3 cosine t times I plus 9 sine t cosine t times j plus 3 sine t times k. And here's a quick sketch of what that looks like. Get this curve going in this fashion. So you've got this cylinder, the x squared plus z squared equals 9. The green axis is the y-axis, so we're kind of looking down the y-axis in this case. It intersects the y equals xz surface. And this curve kind of goes around and back and around this way, if you will.